we're going to now go through and look at how, so we just showed how you can compare two distributions using a histogram. We're now going to look at actual comparing two distributions of the same variable. So looking at a univariate distribution, so just two distributions in the same variable x with different samples, and looking at how we can compare these two things in an effort to try and diagnose problems, to try and diagnose, for example, catastrophic outliers, so that we can recognize that those things are present in the data set and, you know, make our analysis robust to the presence of those failures. Okay. The first thing is the KDE again. And so we've seen in the previous slides, or rather the last week as well, that you can use a KDE, which is sort of a continuous replacement for a histogram, continuous version of a histogram. So again, we can basically take the histogram that we just made from the previous slide, and we can compute the KDE of that particular histogram. And what we find is that the red line here shows the first survey, and now it's very, very clear that there is no information in the first survey out of this outlier peak, because the line is very clearly at 0. And you can furthermore see that the distributions here at low values of the size are almost identical, which I would argue is easier to see with the KDE than it was with the histogram. So the KDE is very, very useful for doing this sort of direct comparison. However, if you had, instead of 2 data sets to compare, rather 20, then having 20 lines over this plot, all of which have slightly different noise and various other things and outliers, can become very, very difficult to understand and interpret. And therefore, it's often useful to not look at the KDEs in this format directly, but instead to look at other types of graphical summarization. Okay, so one such other graphical summarization is what you may remember from high school, which was referred to as the box and whisker plot. And so a box and whisker plot is essentially a graphical tool for summarizing quantiles of the data distribution. And what does that mean? So basically what you can do is you can take a 2 data sets. So here we have the first survey and the second survey. And what you can see is that given the outliers that are present here, it's very, very clear that this isn't super informative with the current y-axis that we have here because of these outliers. And so just to sort of get an understanding of what's happening with these actual box and whisker plots, we can shrink down the y-axis to instead just contain the overwhelming majority of the data. And this is what we see with the box and whisker plot. So what we've got here is the box section of this distribution shows you the interquartile range of the data that you have. Okay, the horizontal bar here is the median. So you have the median and the interquartile range. The whisker, so these dotted lines that lead to these bars, these are depending on how you formulate the box and whisker plot, they are variably a certain fraction of interquartile ranges beyond the mean. So essentially that is to say, if we have, for example, let me go back to just draw something here. So if we have a distribution of data that sits, like this, then our box and whisker plot, so let's just call this X and let's call this N. So our box and whisker plot has the median, which sits here as the bar, the box, which is the interquartile range, and then the dots and the whisker I want to say the whisker extends to the last data point that is 2 interquartile ranges from the median, for example. And that would give me this data point and that data point. And so that's the whisker. That's how the whisker is defined. And you can basically choose that somewhat ad hoc. And then any data point beyond the whiskers is shown as a point. Okay, so you can see here that in this case, the decision that I made for where to put the end of the whisker means that there is an outlier, in inverted commas, very, very near to where the edge of the whisker is. And in the second data set, obviously, we saw that the outliers were very, very far away, and those were our failed mascots. The last thing to note here is the notch that you can see on the box and whisker plot is something that you might not see on all box and whisker plots. And what that notch tells you is essentially the confidence that I have in where the median sits. And so this relates to the uncertainty on the median. And the uncertainty on the median, or rather what's called the 95% confidence region on the median, is defined using this formula here, which is 1.58 plus minus 1.58 times the interquartile range divided by the square root of the number of elements, the number of data points that are in the data set. Now, where this magic number 1.58 comes from is somewhat similar to the normalization coefficient we saw in the NMAD. It comes from what's called asymptotics, and you don't really need to understand where it comes from, but this is essentially the formula for the confidence region on the median, and that's what's shown by the notches here. Okay, so what we can see from the box and whisker plot here is that essentially the localization of the median between these two data sets is within the notches exactly the same. And so according to the median statistics and the interquartile range and the whiskers, these two data sets are identical, except for the catastrophic outliers, which are shown by the points. And that's the interpretation that we want with this particular data set. Yeah. So that's good. The box and whisker plot has done its job. It's told us that nothing has changed in the intervening 6 months between these two surveys, except for the presence of some catastrophic outliers in the second survey. Sometimes, however, the distribution of data won't be simplistic. It might not be Gaussian in the main body of the population. It might be multimodal, for example. It might have multiple populations that exist at different values. We'll talk about that a little bit more later on. And one of the ways that you can make your analysis robust to the presence of very, very strange distributions of underlying data is using, again, the KDE. But instead of using the KDE in the way in which we plotted it before, which is having just a distribution. So if I go back to what my little plot here, no, I didn't plot it. So what we had before, which was just the distribution on the x-axis with our little outlier bump. Instead, what we can do is we can construct what's called a violin plot. And the violin plot looks like this. And what you can think of the violin plot as, I'm going to draw on my own slides here for the sake of explanation. The violin plot is essentially the KDE. So if you were to tilt your head, then this orange histogram, or rather curve here, so this is now X, and this is the KDE on the y-axis, then that is the KDE. That's the kernel density estimate for this data set in height. Yeah, that kernel density estimate is then mirrored about the center of the distribution here, and that gives you what's called the violin plot. Okay, and so if we were to create the violin plot for both the May survey and the November survey, then we see that the May survey has just this peak at low values of the height, and the November survey has a very strong peak at low values and then has these outlier peaks at higher values. Okay, the utility of the violin plot is that it shows the KDE, and it shows the KDE for many different, possibly many different sets of data in a way that is easily digestible. So we can, for example, shrink down the KDE to just be around the plot, the part of the distribution that has the most data. And when we do that, we get this error, this warning message that says, hey, we removed some data when we made that reduction in y-axis. Just be aware of that. And you can see now that these distributions are actually subtly different, but overwhelmingly they look quite similar. One of the really neat things about the violin plot is that you can compound information into the violin plot in a way that is really easy on the eye. It's really easy to interpret. Now I'm using, you've probably noticed, or you might have noticed, I'm using a very strange plotting function here. You might recall from the first lecture, or the 0th lecture as it were, that I discussed how the majority of the plots that I make use this thing called magic axis. The other very, very, very popular tool for making plots in R is this thing called ggplot. Now, I won't go into the details of ggplot now, but if people are interested, then I'm happy to give an additional sort of note on how to use ggplot. And you'll see why it's so popular. It's very, very powerful. The way in which you use it is slightly different than what you do for a normal function call. It's closer to object-oriented programming, or rather pipe sort of things that you might be familiar with from shell scripts and stuff. But this is just to say that we're creating a plot which is using the information from our data frame, which contains our survey data, and we want to plot the survey versus the height. We want to reduce the Y limits to this range. We want to plot a violin plot, and then we want the colors to be classical, and we don't want there to be a legend. And that's what you do to get this violin plot. It's very simple. And the real power of ggplot is the ease with which you can then layer things on top. In that way, it's very much like matplotlib in Python. And so, for example, if I then wanted to add the actual data points, for example, to see where the values lie in each of these surveys on the height axis, then I would just say I want to add geometric points with this particular style, and boom, there they are. So you can see that the KDE is showing you that the data points are starting to peter out here, and that it's basically a solid line in the middle here where there's lots of data. And so you go, okay, well, that's not super useful for me. But wait a minute, we just spoke about the box plot. What about if I instead put a little box plot in the middle here? So that way I've got the KDE and the box and whisker plot all in one. And you can do that again very easily with ggplot by just saying box plot. And there you have it. So now we have the box plot and the KDE together in the distribution. You can see where the outliers in the box plot lie. And all of it is quite easy to interpret, quite easy to understand. So this is the violin plot, very, very useful. The last type of plot that we're going to talk about from memory is what's called the quantile plot. So you'll recall that we talked about the quantile distribution already a couple of times in this lecture and last week. The quantile plot does exactly what it says on the tin. It plots the quantiles of one distribution versus the quantiles of another distribution. And that might seem or sound a little bit strange, but it turns out to be an extremely powerful way of discerning differences between two univariate data sets, two data sets that have the same variable, and you're plotting different samples of them. So again, we can just use base R now to plot the QQ plot. And we can look at the QQ plot of our May survey and our November survey. And what we find is that you see a huge scattering of the data points down here. And then all of a sudden, the November survey jumps to very large heights, and these are our catastrophic outliers. Now, this isn't really easy to understand because the majority of the data have been squashed down the bottom. And so what we can do is we can instead sort of focus ourselves on the 1-to-1 region, which is what this red line is showing. And so instead, we can plot with a fixed aspect ratio. So one step in X is one step in Y. And we can plot it around the region where the majority of the data is. And I've converted the points to a line now. And what you can see is that the overwhelming number of quantiles of the heights of the May survey and the November survey sit on the 1-to-1 line. That is to say that the quantiles of the May survey are the same as the quantiles of the November survey until you get to very large, until you get to the catastrophic outliers, and that's where it flies off to infinity. Now, the utility of the quantile plot is that it encodes a lot of information. more than you probably understand just by looking at this example. So let's construct a couple of just fake data sets to give you an idea of what the quantile plot shows. So let me show you, let me make again just a number line here on my little pad down on the bottom right. Let's call that, X, and we'll put 0 in the middle. And the first data set that I've constructed is just a Gaussian with a center at 0. Okay. The second data set is a Gaussian with a mean at -2, and the third is a Gaussian with a mean at 2. Okay, so these are our 3 data sets: 0 mean, negative mean, positive mean. And I'm then going to plot the QQ plot for these different data. And what you can see is that if I plot the 0 mean versus the positive mean first, that the 0 mean is on the x-axis here, the positive mean is on the y-axis, and you can see that just by the values. I haven't plotted the labels on the x and y-axis here, which is extremely naughty of me. I'll make sure that I change that in the lecture notes so that you don't learn bad habits. But that is to say that you can see that the positive shift in the mean has caused a shift with respect to the distribution and the one-to-one line. You see the opposite shift when you use the comparison between the 0 mean and the negative mean data. And if we look at the difference between the positive mean and the negative mean, then that shift gets greater again. So a shift in the mean causes a very significant lateral movement away from the one-to-one line in the QQ plot. Important fact. The second thing we can do is say, okay, that's the mean. What about if the distributions have different dispersion? So now we can construct 3 new data sets which have a standard scatter. So here we're now, let me remove these plots here. Oh, no, not going to do that. Instead, I'll just draw them up here. So let's now look at a different data set where we have, I shouldn't have done that. Anyway, we have 0 here again. And this time we have one data set which has a standard dispersion, one data set which has a very small dispersion, and another data set that has a very broad dispersion. Okay, those are our 3 data sets. And so the standard scatter data set, we plot against the small scatter data set. And what we find, again, is that now instead of shifting away from the one-to-one line, what's happened is the tilt has changed in the one-to-one line. Okay? And again, if you do this the same with the standard scatter and the large scatter, again, you see a change in the tilt of the QQ plot with respect to the one-to-one line. And that tilt becomes more significant if you compare the large scatter and the small scatter. So this is related to the difference in dispersion between the 2 data sets. So the deviation with respect to the distance to the one-to-one line dictates a shift in the mean, in the median. A difference in the slope with respect to the one-to-one line dictates a difference in the dispersion. And the last thing that we can look at is what happens if we have outliers. So we can construct a normal distribution with data, which is just a Gaussian, and then we can construct the same Gaussian, but we can add in 100 random outliers. And we plot the QQ plot of this distribution, and we see this happens. So you have a incoherent deviation away from the one-to-one line caused by a difference in the outliers of the 2 populations. So the QQ plot is extremely powerful. It tells you the difference in mean statistics, median statistics, the standard deviation, the scatter, the dispersion, and the outlier rate, all in a very, very visual manner. So I can now construct, yes, absolutely. So the question is that can the size of the 2 samples be different? And as you can see, what I've done here is I've actually created 1,000 elements in the first data set and 1,000 plus 100 elements in the second data set. So they can have totally different lengths, numbers of observations per sample, and they still are it's still totally perfect, totally fine to use. And that's because the quantiles are calculated of the data set, not using the individual values within the data set. Great question, great question. So the last thing that I'm going to do is I'm going to tell you that I've constructed a fictitious data set. My fictitious data set has value y, is called y, and the expectation that we have as astronomers going and physicists going into our analysis is that the distribution of y should have the form of a Gaussian with mean 0, standard deviation 1. And so what I'm going to do is I'm going to construct a model distribution of data which has mean 0, standard deviation 1. And then I'm going to compare the QQ plot, or can construct the QQ plot for that model distribution of data and the true data set Y. And this is what I get. And the question then becomes, what, given this plot alone, can you conclude about Y? And so we can basically go through and we can say, okay, there's a slight offset with regards to the mean, to the distribution with regards to the one-to-one line in absolute terms. So there's clearly a slight difference in the mean and the median of these two distributions. So the Y data don't have a mean that is equal to 0. First things first. Second thing, the slope of this line is not equal to 1-to-1. So there is a difference in the scatter between the data and our assumed scatter of 1. Second point. Third point, we see an incoherent deviation from 1-to-1 at high and low values of the QQ plot, which demonstrates that there are outliers that do not fall in the Gaussian model that we've constructed. And so with this plot alone, we can already start to diagnose a bunch of really important things about our data set. So the QQ plot, very, very important. We're going to see a lot more of it a bit as we go through the probability section of this course. Great. I hope that's been clear. We're now going to leave comparisons of distributions of one variable behind, and we're going to start looking at distributions of two variables or more variables. And the primary way that you compare distributions of two variables, so how do I compare observations in X and Y, is by plotting what's called the scatter plot that you've all absolutely seen at some point, because I plotted it in the last 2 weeks. And so what you can see here is I've created a data set. My data set is made up of, again, just Gaussian data, random normal data of 1,000 elements. And it has one variable X, which has a mean of 0 and a standard deviation of 1. And it has a variable Y that is also Gaussian, but has a mean of 100 and a standard deviation of 1 as well. And what you can see is that you have a Gaussian distribution, a random sort of circular scatter plot. But I mean, looking at this, it actually looks like it might be a little bit squashed, right? So if you didn't know that these two data sets came from something which had the same dispersion, you might look at this visually and say, oh, well, that could be slightly different dispersion. But that's kind of a trick of the eye because we're not using the same range on the X and the Y axis. We haven't used the same dynamic range, the same aspect ratio in this plot. So the first thing that you want to do is always be aware of the scales of the axes. Because if it turns out the y-axis covers 10 more units than the x-axis for data that you think should have the same dynamic range, then you can trick yourself into finding correlation when there is none. Talk a bit more about that in a minute. So the first thing you can do is always set the aspect ratio to 1 for data that you think should have the same dynamic range, that should have roughly the same scatter. And if we do that, indeed, we see that this then becomes a little bit more sensible and looks a little bit more circular spherical. For data with very different aspect ratios, using a fixed aspect ratio of 1 doesn't work for obvious reasons. So the question is, what do we do in order to measure or look at the relationship between variables that have very, very different dispersions in one variable and the next? Well, the first of which you can do is you could plot with two different y limits on the X and Y axis and tailor those to your own benefits. So that's the first thing you could do. You could tailor the X and Y axes by hand in order to get sort of a roughly similar sort of dynamic range. Or you can plot the data in what's called standard coordinates, or if you're a machine learning person, then this is what's called whitening the data. And so what standard coordinates refers to is taking a data set and transforming each variable within that data set so that it has a mean of 0 and a standard deviation of 1. And using the standard coordinate system, you can then compare directly by eye relationships between different data sets, between different variables rather. So again, we can take that same data set that we just had, which has a very different dynamic range. So we have, a standard deviation of 50 in the y variable and a standard deviation of 1 in the x variable. We can convert that distribution to standard coordinates just using the scale function, which converts every variable in the data frame to a standard coordinate system. And we can then plot the standard coordinates, and lo and behold, everything looks honky-dory again. Everything looks good again. So standard coordinates are very useful. We're actually going to use these quite a bit later in the probability section of this course, but we'll talk about that a bit later. The next way that you can plot distributions of two-dimensional data in a way that's useful and interpretable is using, once again, the KDE. So you'll hear that KDEs are quite popular. They're quite useful. They have a lot of uses. And this time we're going to plot the two-dimensional KDE. So we're going to plot the kernel density estimate using a two-dimensional kernel in this case, which is a Gaussian, a two-dimensional Gaussian. So it has a bandwidth in X and a bandwidth in Y. And we're going to plot an inbuilt data set within R, which is called the faithful data set, which shows the correlation, or rather a set of observations of the time of eruption of the Old Faithful geyser in Yosemite National Park in the US versus the time that you have to wait until the next eruption after that eruption. And the first thing you can see is that this thing is bimodal. And the second thing that you can see is that it's, there's some trend here, right? And so plotting the kernel density estimate is useful because there's lots of data in here that you then want to smooth out into a distribution that is useful to interpret. And so you can really pull out the bimodality by eye using the kernel density estimate. This KDE, 2D KDE, I've made using one of the magic axis functions, magcon. But as always, ggplot has another, and also is able to do the kernel density estimates. And the way in which you can do a kernel density estimate in ggplot is using this just geom density 2D. And so here I've plotted the scatter plot of the data set from Old Faithful, and then I've overlaid the two-dimensional kernel density as contours. If instead of contours, I wanted to use, for example, an image like we had sort of in the background of the magplot thing, the magic axis version, then we would use this 2D density filled, very simple again, and you get this really sort of pleasing, aesthetically pleasing plot, which I'm sure will please the Python affiliates in the audience, because this is sort of the standard Python color bar that you can see here. And you can then obviously overlay both. You could have both, for example. So you could have the 2D kernel density, the scatter plot, and the contours all together. All right, so this is just a demonstration of how you can use the kernel density estimate in 2 dimensions as well as in 1 dimension to demonstrate the relationships between variables. And again, it's very, very useful at pulling out things like bimodalities or multimodalities in the data. So data that have multiple peaks in the density distribution. Great.